So hello everyone, welcome back on another video on digital signal processor. In this video, we are going to learn about the serial communication interface for C2000 microcontrollers. So here in this slide, the sum of the register set for the serial communication interface is shown, and these registers are as follows. So it is having the serial communication control register, the control register 1, and the baud rate register, control register 2, status register, receiver emulation data buffer, receiver buffer, transmit buffer, P4 transmit register, P4 receive register, P4 control register, and priority control registers. So in subsequent slides, we will be looking each and every registers in detail. So the first register in the series is that the communication control register. The communication control register will be defines the character format, protocol, communication modes used by the serial communication interface. So this is the basic communication control register, and it is a 16 bit out of upper 8 bit are reserved. The first register in the series is that the stop bits, and the stop bits will define the number of stop bits to be transmitted along with the data frame. So it could be either 1 and it could be either 2. So when writing on this bit, a 0 will be defined as number of bit to be transmitted, stop bit to be transmitted as one stop bit, and 1 means the two stop bit to be transmitted along with the data frame. The next register is even and odd parity. So if this parity enable bit is 1, then we can able to select this bit as either it could be even parity or odd parity. The next register is parity enable. So this bit enables or disable the parity functions. So writing on this bit once it will enable, otherwise it will disable the parity enable functions and the even or parity. So the loopback function is nothing. It enables the loopback test mode where the TX pin is internally connected to the RX pin. So for the hardware, the TX pin is internally connected to the RX pin. So whatever you are transmitting, it reverts back to the same the receive buffer. So you can able to test your transmission and receiving the data from the same devices. And address and idle mode. This will select multiprocessor communication mode. Either it could be the idle line or address with mode. And idle line is used for RS-232 type of communications. Next is HCI characters. So the character length is the 3 bits, and this bit selects the HCI character length from 1 to 8 bits. Character of less than 8 bits are read justified in RX buffer and RX EMU, and are padded with leading 0 in RX buffer. So for example, if you are giving the 000 to this bit, that means we are able to give the 0 data bit. That means we are able to giving the 0 data bits. And if you are writing this bit as 1, 1 and 1, that means we are able to use the 8 data bits. So the next register in the series is control register, and this register controls the receiver transmitter enable, TX backup, sleep function, and XCI software reset. So this is also a 16 bit, out of upper 8 bits are reserved, and the first register is RX error interrupt enable. So this is the HCI receive error interrupt enable. So setting this bit enables the interrupt if RX error bit, the XCI RX ST. So the status bit, if the status bit becomes set because of error string. So whenever this bit will be equals to 1, in this case it will generate the interrupts. So this bit will be generate the interrupts. So by making it 1, that means receive error interrupt enabled, and by making it 0, that receive error interrupt is disabled. So when configuring the SCI communication control register, the SCI port should be had in inactive states. So whenever we are configuring the communication control register, your SCI should be in inactive states, and this is done using the software reset bits of the this SCI control register. Writing 0 to this bit initialize and hold the SCI state machines and operating flags at their reset conditions. And then SCR communication control register can then configure and afterward re-enable the SCI port by writing 1 to this bit. And whenever the system reset happens, the software reset bits will be equals to 0. So writing 1 on this bit release from the SCI, release from reset, and writing 0 means reset the SCI. So reset it, once we have reset the SCI, we can configure the communication control register, and writing 1 we can release it from reset. And the next register, and what happens during the reset happens. So in that case, the TX RDY TX empty bit will be set, and the other bits of the other control register will be reset. So now the TX bit will be SCI transmit backup method select. So whenever we are transmitting the data, so how it will be backup. So this bit controls the selection of data transfer features. Either it could be the idle line or address bit mode. So and this bit is not cleared by the software set. And how can we clear it? It can be cleared with the system reset, or we can transfer the TX reg to backup transfer, backup temporary flag register. So writing 0 on this bit will be select the no backup mode, and writing 1 will be select the backup mode depending upon the communication control register, because in the communication control register we have made the address line and idle line that could be either 1 and 0. So in the idle mode it will be 0, and address line mode it will be 1. The next register is the sleep register. So as this register will control the transmission data transfer feature, the sleep function will be control the receive functions. That means it brings the SCI out of sleep. Although the receiver still operate when this bit sets, however the operation does not update the receive ready bits error status bit unless the address bit is detected. So the next register is TX enable and the RX enable. So data transfer to the SCI TXD pin only when TX enable is set, and if reset happens, the data transfer text is halted, but all the data that has been written on SCI TX buffer is sent. And if data is written on serial a transport buffer when TX enable is disabled, this will not able to transfer the data if TX enable is enabled later. So it will help to enable the transmission, and writing 0 means it will be disable the transmission. And the same way SCI receive enable, and data is received on the RxD pin and sent to the receiver shift registers and then receive buffer. And this bit enables or disable the receiver. So writing is 1 on this bit will be make a receiver enable, and writing 0 make it this bit as a receiver disable. The next register in this case in this series is that board register. So these are two upper and lower board registers, and this will define the baud rate of the serial communication interface. So the baud rate can be calculated by the help of these two equations. If BRR is 1 to 65,565, and here LSB clock could be the low speed clock, it could be 100 megahertz and it could be the 50 megahertz, depends upon how you have configured this LSP clock. And the baud rate register value is the actual register, that is the total 16-bit register. So once you know your SCI baud rate, for example, it is 9600 baud rate and LSP clock is 100 megahertz. So the baud rate register can be calculated by keeping this value. So the next registers in the series is that the SCI control register 2. So these control registers enable the receive ready, break detect, transmit ready, interrupt, as well as transmit ready and empty flag. So this is the register set for the control register 2. So the first set of register is that TX RDY bit, TA transmit ready, SCI transmit ready, and this indicates that the XCI TX buff is ready for the another character. So when the data is written on SCI TX buff, this bit clears automatically. Okay, so whenever transmit is ready, or whenever data is written on this TX buffer, so this bit will be cleared automatically. And when this bit sets, the flag generate the interrupts. So whenever the data will be available on the SCI TX buff, or data will be available for transmission, this flag will be generating the TX interrupt. And when TX interrupt will generate, if interrupt enable bit is equals to 1, and that set equals to 1. So then another way to set this bit is by software reset or the system reset. So 0 means the SCI TX buff is full and 1 means XCI TF buff is empty. So this is the flag register, and during transmission or receiving the data, okay, so we have to check the whether our transmit buffer is full or the transmit buffer is empty, and this will be we will be using in the polling method when we are not using the interrupts for the serial communication interface. So the next is TX empty. So this flag indicates that content on SCI TX buff and shift register, and the software reset and system reset sets this bit. So whenever the software reset and system reset happens, this bit sets to 1. So this bit cannot generate the interrupt, but this bit can be used in the polling method when we are not using the interrupt driven mode. So 0 means TX buff or shift registers are loaded with data, and 1 means transmit buffer and shift registers both are empty. So whenever this will be 1, that means the transmit buffer and shift registers both will be empty. The next register is the RX receiver break interrupt enable, and the 0th bit will be TX interrupt enable. So receiver buffer break interrupt enable. This bit controls the interrupt request, and when you are writing 0 to this one, that means disable RX RDY break detect interrupt, and 1 means we are enabling the receiver ready and break detect interrupts. So these bits will be enable or disable the SCI receiver or SCI receiver interrupts, and this bit will be controls the SCI transmit interrupt. So the next register is the SCI RX HD register. So receiver status registers. So this is the receiver status registers. It is 7 bit, and out of and this is the completely flag status flag registers. So out of 7, out of uh, this bit, 2 flag registers can generate the interrupt. Okay, so whenever the flag registers will be set or reset, that can be generated interrupts. The first register is RX error. So receiver error flag. If any flag are set, so any of the flag registers, for example, FE timing error, OE overrun error, PE parity error, and break detection error. So if any of the error happens, this receiver RX error will set to 1, and if RX error will set to 1, that means it can generate an interrupt. And when it will generate an interrupt, if the control register 1, SCI control register 1 dot bit dot 6 equals to 1, when interrupt will be enabled, then it can generate the interrupts. The next register will be RX-RDY flag. If new character is ready to read from RX buffer, that means the character is received and that is ready to be read. That means this register is going to be set, and that can also generate the interrupts. And when it will generate the interrupt, when this bit will be equals to 1. And the break detection conditions. So if break detection condition occurs, so what are the meaning of break detections? That means your SCI RXT pin will be low for minimum 10 bits. That means it will be set to 1, and it will also generate the interrupt if RX break interrupt enable bit will be 1. Next is the framing error. So if expected stop bit is not found, that means the framing error bit will be set to 1, and this is the status register. Overrun error, that means if previous character is not read completely by the CPU, it means it lost, then this error will happen. Parity error. If number of 1 and its parity bits are mismatched, and this flag will be set. RX backup. 1 in this bit indicates that detection of receiver backup conditions. The next register is SCI RX EMU registers, and this is emulation buffer data register. So this is the just emulation purpose, and it cannot be implemented physically. The next register is SCI RX buffer register. So this is the block diagram of the SCI RX buffer. So whenever data is receiving on the input port of the serial, and if RX enable and RX bit will be set, then this bit can generate an interrupt. And whenever RX RDY pin will be set and RX or this bit will be set, then that can be generate the interrupts. So it is the SCI FIFO framing error flag bit, and this is the SCI FIFO parity error flag bit, and this is the receive character bit. So character will be, this is the receive character that we are receiving from the serial line. The next register is the SCI TX buffer register. So the transmit data buffer, and there we are sending the data of 8 bits, and this can also generate the interrupts whenever the data is transmitting over the serial line. And when the TX interrupt enable pin is set and the TX RDY pin will be set, it can generate the interrupts. The next register is SCI FFTX FIFO transmit registers. So this is the first register is SCI RST pins. That's the SCI reset pin. So by setting this pin to 1, that means if we are enable the operations. The next register is SCI FFENA. That means SCI FIFO enhancement. By keeping this bit as 1, we are enabling this FIFO, and by keeping it bit 0, that means we are disabling the FIFO. And transmit FIFO reset. By making this bit as 1, that means we are enabling the operations. And by making this bit as 0, that means we are resetting the pointer to 0. The next bit is TX FIFO status, and these are the status registers, and this bit only read only bits. So that means that when this bit is all the pins are 0 0 0 0 0, that means TX34 is empty. If this is 1 and remaining bit are 0, that means the FIFO has one word. So by writing these things, we are able to transmit the data on the FIFO. This is the lower FIFO TX registers. So here the seventh bit is transmit FIFO interrupt flag. So whenever the interrupt happens, this bit will be equals to 1, and whenever interrupt not occur, this bit will be equals to 0. So by checking this interrupt pins, we can go to the ISR. The next register is TXFFINT cleared. So TX FIFO interrupt flag cleared. So 1 means we are able to clear this bit, and 0 means this doesn't have any effect. The next register is the TX FIFO interrupt enables. So it can be make it 1 and for to enable, and it can make it 0 to disable. Another register is TX FIFO interrupt level. So the interrupt when TXFFST 4 to 0 and TXFFIL 4 to 0 matches. The next register is SCI FFRX pins. So this bit is RX FIFO overflow flag, and whenever the overflow happens, this bit will be 1. So this is the flag registers and read only registers. This is the RX FIFO overflow flag clear, and this bit will be RX FIFO reset, and this bit will be RX FIFO status, and these are the read only registers. And these are the similar as the SCI FFTX register. And this is the lower 8 bits. So the next register is SCI FFCT register, FIFO control register. So here it is the ABD auto baud rate detections, and this is also read-only registers. That means auto, when writing on this bit, will be seeing that the auto uh, baud rate detection has been completed, and when this flag bit is 0, that means auto baud rate detection is not completed yet. So the next bit is ABD CLR, auto baud rate detection clear bit. So 1 means the auto baud detection flag has been cleared, and 1 means it is not cleared yet. CDC means calibrate A. So when you are sending the data, either capital A or small a to this bit, to the serial line, that means it will automatically enable the auto baud rate alignment. So the next register is FFTX-DLY. So the time delay between every transfer from FIFO to transmit shift register in number of SCI baud clock cycle. So this will be 0 to 255. The next register is the priority register. So SCI PRI determines what happens when emulation suspend or event occurs. So for example, when debugger hits the breakpoint, The peripheral can continue whatever it is doing in the free running mode, or if in stop mode, it can either stop immediately or stop when current operations is completed. So writing on this bit, when you are writing to 0 to this bit, that means it will immediately stop and suspend the operations. When we are writing to this bit is 1, then complete current receive and transmitter sequence before stopping. And writing on 2 or 3, it will be continuously running. That means the data can be sent continuously without suspending the current operations. So in the next video, we will implementing the serial communication protocol using the Code Composer Studio, and we will be dealing with the pooling method first. So in the pooling method, we won't be enable the interrupt, and further we will be looking the interrupt driven serial communication interface. So here we will be using TMS 320 F28379D microcontroller, and this also applicable to 28335 microcontroller, and is also applicable to 28388D microcontroller. So anyhow, this will be applicable to any kind of C1000, C2000 microcontroller. So if you have any comment regarding this, you can comment me on the comment section, and don't forget to like, share and subscribe my channel. Thank you.